Okay, welcome back. So, in my last class, I was doing fundamental theorem of line integrals, right? And after that, what we did, we found out when, you can express a vector function as a scalar potential, right? And the condition for this was given by if this line integral, this is independent of the path in a region D where the curve C lies, so then we can have f of this form, and then from here f being conservative, we have found out that if your f equal to your pi plus qj, so then your del p del y, so this is equal to del q del x. Okay. So now the next question is, we have found out that, see, if f is conservative, then this happens. Okay. So the next question is, if this condition is satisfied, does that mean that it is going to guarantee me that f is conservative? Okay. So in order to answer that question, we need to learn some concepts. Okay. So the first thing is about a simple curve. What is a simple curve? Okay. What is a simple curve? Okay. So what is a simple curve? I mean, if you consider a curve either in the plane or 3D space, if the curve does not cross itself, then we say that it is a simple curve. Okay. So, for example, I mean, if I consider this curve, this one is not a simple curve. Okay. So this one is simple. This one is simple, but this one is not simple. This one is not simple. This is not simple. So this one, say, suppose, I mean, if this kind of curve, they have the parameterization, say, your RT, where T lies between A and B. So if a curve is not simple, then what is going to happen? There exists your T1, T2 lying in the open interval A, B, such that somewhere I am going to get RT1 equal to RT2. Is it okay? Fine?
Yes.
Right? So this is about simple curve. So now let us see when does a curve become more simple and closed. So basically a curve, I mean, if a closed curve is this, okay. So this is an example of a simple closed curve. But on the other hand, this is also a closed curve. But this is not simple. Right? So what we will be interested in? We will be interested in your simple closed curve. Okay. Now the next concept is that of a simply connected region. So this concept, in future also, being engineering students, when you are going to study other stuff, and particularly in complex variable also, when you are going to do 201 over there, this concept is going to come quite frequently. Okay. So what is a simple connected region? Say, suppose we consider a region B. we consider a region D. This maybe for the time being, let us assume that this is a two-dimensional region. Okay. So then, if I consider any simple closed curve here, okay, so suppose, right? Okay. So if this simple closed curve, it encloses points only belonging to this region D, then we say that D is a simply connected region. Okay. So for the time being, whatever I have drawn here, it is not very clear. But if I draw, say suppose this region D, suppose it is nothing but the shaded portion. Okay, the shaded portion is the region D. Fine. Okay. So then, what may happen? Now, obviously, this part does not belong to D, right? Now, if I consider a simple closed curve here, again, see this blue curve, it belongs to D, right? But you can see that the blue curve, it is going to enclose points which do not belong to D. Is it okay?
Yeah.
Right? So basically, when does a region, stop becoming a simply connected region is that when it has some holes. When it has some holes in it. That's it. Okay. Whenever you have some holes, then maybe you may have more than one hole, right? So then this kind of region, they are called. In fact, they are not simply connected region. They will be called partially connected region. Later on, you are going to see. Okay. So now what I'm going to do, I'm simply going to run through this slide, and I'm going to simply show you the theorems related to that. So if you look at the theorem 6 here, let F given by Pi plus Qj be a vector field on an open simply connected region. I have already told you what is an open region. Okay, yesterday I had defined that. Okay, although initially I made a mess of that. Okay, later on I corrected that. So open simply connected region D, and suppose P and Q, they both have continuous partial and partial derivative, and this condition is satisfied. Del P del Y equal to del Q del X throughout D. So then F is conserved. Okay, so this I am not going to prove, but this one I am going to use. This one I am going to use later on also. So let us do a couple of exercises. Okay. So just a minute. In case I have. I don't know why this screen is coming over here. Okay. Just a minute. No, it's still coming over here. I don't know how it got changed there. Okay, anyway. Let us try to work out a couple of examples. Say, consider this one. Exercise your F equal to x minus 2j. Okay, so is it a conservative vector field? So for that, what you have to do? Simply, this is P, this is Q. What you have to do? You, pardon?
We cannot see the board.
Oh. What do you see? Nothing? Just a minute.
I can see the slides.
You can see this slide.
Slides.
Okay, just a minute. Let me just. I don't know how did it get. Just a minute. Okay, I have stopped sharing. Can you see it now?
Yes.
Okay. Something happened. Okay, fine. So let us consider this example. Let us consider this example. So f is a vector field given by this. So the question is it conservative? So what you have to do now here, the first component is P, second component is Q, right? And one thing, just a minute. Yeah, fine. Second component is Q. And remember, whenever we are talking about this theorem of conservative vector field here, so this theorem, they are related to, vector value function considered in two-dimensional space. Okay, because here we are only considering the condition of del p del y equal to del q del x. Okay, fine. So now, what is your del q del x? Del q del x is 1, right? And your del p del y, this is simply -1. So they are not equal, right? So this is not a conservative vector field. Okay. Now let us consider another one. So f equal to your 3 plus 2xyi plus your x squared minus 3y squared j. So now the question is it a conservative vector field? Yes or no?
The condition del p del y equal to del q del x is satisfied.
So,
but we will have to check other conditions.
What is that condition? Yes, you are in the right direction. Other condition is that the reason on which we consider it, right? That has to be an open, simply connected reason, isn't it? Right?
Yes.
Okay. So now the thing is that I can consider this function f. I can consider this function f over whole R2, isn't it? Right?
Yeah.
And this is going to be an open, simply connected reason.
Yeah.
Isn't it? And here you can definitely see, that del p del y equal to del q del x, because your del p del y, this, if you take derivative with respect to y, this is 2x, and here also your del q del x, that is going to be equal to 2x. Okay. So now the next question is that we have found out that this is a conservative vector field. So that means there must exist a function small f, it is a scalar function, such that your capital F are equal to greater. Is it okay? Fine. So now, how to find out that scalar function v? How to find out that scalar function f? Now the thing is that one thing you have to see that what utility we are going to have by expressing your capital F in terms of greater. We'll see that later on. But let us try to find out small f. Okay. So now, if f has to be of this form, so that means this is del f del xi, del f del y j. So if we equate the respective components of f, then what we must have, your del f del x. So this is equal to 3 plus 2xy and del f del y. This is equal to x square minus 3y square. Okay, fine. Now, if I integrate this relation, I mean partially with respect to x. So then from here, what I'm going to get? I'm going to get f as a function of x and y. That is going to be 3x plus x square y plus some constant. But the thing is that here, while
Y is constant.
I mean, yes, partially integrating with respect to x, we assume that this is independent of y. So that is why that constant must be a function of y. Okay. So now from here, if I again, I mean, differentiate partially this function with respect to y, so then you will see that this is what x squared plus 5 prime y, and we have been given that this is equal to x squared minus 3y squared, right? So that means your 5 prime y, that must be equal to minus 3y squared. So that means 5y, because this is simply a function of this single variable y. So that is why once we integrate it, this must be y cube plus some constant c. Okay, fine. So that is your small f of xy equal to 3x plus x squared y minus y cube plus c. Okay. Now let us come to one interesting. Just a minute. Okay, I already have that, so I can erase this. Okay, fine. Now, suppose I mean, like say you have already been given like f equal to 3 plus 2xy x squared minus 3y squared, right? F is giving us this. Now, suppose you want to evaluate this line integral. Evaluate this line integral. Okay, where your c is given by this rt equal to your e to the power t sin t I plus e to the power t cos t j. E to the power t cos t j. Okay. So, in fact, I'm trying to come to the utility of. I'm trying to come to the utility of using capital F as a conservative vector field. Okay. You will see. Now, say if I want to evaluate it directly, and of course here t lies between 0 to 5. I hope t lies between 0 to 5. Okay. So now if I want to evaluate it directly, so then this is simply what this is going to be. This is going to be p dx plus q dy. Is it okay? Fine?
Yeah.
Yes? So then what is going to happen? I would have converted it into the parameter t. So in order to do that, I mean, you see that p is your 3 plus 2xy. So this is 3 plus 2xy. So it is going to be to the power 2t sin t cos t. Okay? And dx is again going to be derivative of this. Derivative of this is going to be your e to the power t sin t plus e to the power t cos t dt. Are you getting the point? Right? And again, your this plus again your q in terms of t, and again dy again in terms of t. Is it okay? And then what you have to do? Again, t going from 0 to 5. right? That is going to be quite a lengthy computation, although you will be able to work it out. But if you notice, now I am going to have some product here. I am going to have some product here. That is going to make the integrand more complicated. Are you getting the point? Right? But on the other hand, because I already know that capital F, it is a conservative vector field. So that is why what I can do, like I can use fundamental theorem of line integrals. So what that is going to do to me, so now see, if I want to find f dot dr, so you have already found out that this is f is grade f dot dr, and by fundamental theorem of line integral, what it becomes, f fine, isn't it?
Yeah.
So that means it boils down to find out the value of f corresponding to when t equal to 0 and t equal to pi. Is it okay? So f of xy, if you convert it into, t e to the power t sin t plus e to the power 3t sin square t cos t minus e to the power 3t cos cube t plus c. And you don't need to worry about that constant c. That constant c, you don't need to worry about it. Now, so this is simply going to be what? R pi f r 0, right? So corresponding to pi, what is going to happen? The terms involving sine is going to vanish, isn't it? Right? And again, your cos pi is -1, cos cube pi is what? -1, right? So this is going to give me, e to the power 3 pi plus c, right? And at 0, this is simply 1, and e to the power 0 is also 1. So it is going to give me this value as what? -1 plus 3. So finally, the answer is e to the power 3 pi plus 1. Is it okay?
Yeah.
So that means making use of the fundamental theorem of line integrals and the fact that the integrand can be expressed as a gradient function. The integration is much more smoother. Okay, so that is the utility of it. So next, yeah. So just a minute. Yeah, fine. I think I'm done with this particular thing. So the next thing I'm going to do is Green's theorem. Green's theorem. Okay. So okay. So before that, again, we need to learn some more concepts. Okay. So what are those concepts? The very first thing is about positively oriented curve. Okay, positively oriented curve. So here we are going to deal with simple closed curve. We are going to deal with simple closed curve, and the region bounded by such curve. So basically, what here I am doing, I am considering a closed curve C which bounds the region D. Okay? Up to this it is fine. You already know these concepts you have already learned. The next thing is that this we are going to talk C as a positively oriented curve. Positively oriented curve. So what is this? What is the meaning of this? What is the meaning of this? Is the meaning of this is only anti-clockwise? Because so far we have learned that whenever you move in the anti-clockwise direction, we assume that that is the positive direction. Is it so, or is there something else? Of course, in this particular case, definitely, anti-clockwise is fine, but it is more than that. What is that more than that? Is that whenever you move along the curve, okay, so like say you can move along the curve in the direction shown in the arrow head, that is anti-clockwise in this particular case, or you can move in the clockwise direction. But the thing you have to remember is that whenever you are moving along the curve, the region under consideration, it must be towards your left. It must be towards your left. So if you are moving in this direction, so then if these are your two hands, these are your two hands. So this region D is always going to be to your left. Are you getting the point?
Okay.
Yes?
Yeah.
Fine. So that means say I will come to that later on. Say suppose I am considering a region bounded by two curves. Region bounded by two curves. Say okay, the outer region it is fine. So then, but if now I consider the inner region, so then if not inner, if I consider not the inner region, if I consider the inner curve, so then what is going to happen? For the region under consideration to be on your left, you must take the clockwise direction here, isn't it? You must take the clockwise direction here. So in this particular case, for this curve, the positive orientation is going to be the clockwise direction. Is it okay?
Yes.
Fine. So that is the meaning of positive orientation. So I would simply like to show you the Green's theorem. You can see it, right? Yeah. So this is Green's theorem. Okay. So here, firstly, we are talking about, curves having positive orientation. So here you can see that this one is having positive orientation. And of course, we are talking about a simple closed curve which bounds the region D. So here you can see this is positive orientation and this is negative orientation, because here you can see that the region under consideration is always towards your right. Okay, fine. So okay, this is the Green's theorem. This is the Green's theorem. See, please have a look. Please carefully look at the statement. So let's see a positively oriented, piecewise smooth. Okay, it doesn't necessarily be, completely smooth throughout. It is piecewise smooth, simple closed curve in the plane, and let D be the region bounded by C. And if P and Q have continuous partial derivatives on an open region that contains D. So basically, D is a part of an open region. Okay, fine. So then you see what happens. The line integral P dx plus Q dy along the curve C, it becomes the what? It becomes the surface integral.
Double
Isn't it?
integral.
Yeah, it becomes the surface integral or this double integral. I mean, given by that. Okay, fine. So, what you have to appreciate here is that. So, basically, this theorem, it is telling you C P dx Q dy. So, this is equal to P your del Q del x minus del Q del y. Your dA. See, you may be thinking why we are not writing dA as dx dy. You can still write like that because here I have already used dx dy. In fact, here dA is going to be dx dy. Okay, and now in the statement, what they are telling you is that I mean C is a positively oriented, simply closed curve, and it bounds the region D. Okay, so that is the thing. And it is also saying that D belongs to say some region D1 and D1 is an open region. That's okay, fine. So now the proof of this for general region is going to be difficult, but what I would like to do that you can do it for simple reasons. But what is a simple reason? You can do it for a simple reason. So what is a simple reason? Of course, I am talking about reason in R2. A simple reason is one which can be expressed both as a type 1 and type 2 reason. Both as a type 1 or and type 1 and type 2 reason. Okay. So here what I'm going to do, I'm going to prove it for simple reason. Okay. So for that, now, but before that, let me tell you another thing. See, because we are considering C to be a closed curve, so that is why sometimes this symbol is also used. Sometimes this symbol is also used. And sometimes what they do, I mean, in order to denote that, I mean, C is the boundary of D, they also use delta D or C. Okay? So please don't get confused. I mean, they are all the, I mean, same, they denote the, same curve C. Okay? And this one is used when C is a closed curve. Okay? Fine. So, I'm going to prove this for simple reason. Now, see, if I can somehow prove that, your and if I can prove this to be dA, my job will be done, right? Right? Proving these two is suffice. Isn't it?
Yes.
Fine. So that's what we are going to do. Now, I mean, I'm following Stewart's book, but one thing is may confuse you that I want to tell you. So, okay, see what Stewart did in order to prove this part. He considered D as a type 1 region. Okay, and in order to prove this part, he has considered D to be a type 2 reason because of the fact that the very definition of simple reason is it can be expressed as both a type 1 and type 2 reason. So basically, it is going to be, I mean, if it is going to be something like this, if it is something like this, isn't it? This I have considered as type 1 reason, right? If this is A, this is B, I can consider what? This curve to be your G1x, okay, and your this curve to be G2x, isn't it? Or what I can do for the same yes, I can use this interval, right? And I can consider now these to be my F1y and the yellow, these to be my F2y, isn't it? Is it okay?
Yeah.
Fine. So simple reasons is going to be something like that. But what could be confusing for you is that, I mean, because this becomes, I mean, too easy. So that's why what he did, I'm telling you, when he has considered D as a type 1 reason, he has drawn the figure something like this. He has drawn the figure something like this. So what he has considered D to be this region, and bounded by the curve C, where C is the union of, he has taken C1, C2, C3, C4. That is what he has done. Okay, but please don't get confused about it. Please don't get confused about it. Even without C1, just a minute, C4, C2 also, you can easily do the proof. Okay, fine. Because this is a type 1 reason, you can consider it. So that is why the figure is drawn like that. But the actual situation is, if it is of both type 1 and type 2, then it is going to be like the way I have explained just previously. Okay, fine. So now, if this is my reason B, which is bounded by the curve C, which is nothing but the union of C1, C2, C3, C4, sorry, C3, C4, and if C1, say suppose it is given by G1x, and C2 is given by G2x, and suppose it is x lies between this. So basically, D is the region given by this xy, such that your x lies between A to B and y lies between your G1x, sorry, G1x and G2x. Okay, so how to go about it? Okay, so firstly, what I'm going to do, I will try to dA. So dA is simply okay. Okay. Fine. So now what I'm going to do, say, please don't, I mean, look at del P del Y as something which is very difficult. Just simply look it as some function of x and y. So had it been some function of x and y, so what would we have done? I mean, D being a type 1 reason. So firstly, I have integrated it between G1x and G2x, right? With respect to dy, and then I would have integrated it with respect to x between A and B, isn't it? Fine. So Is it okay? Fine?
Yeah.
Yes.
So this is equal to your A to B, and you know that this is simply something like dp, isn't it? So this is simply your p x g2x minus p x g1x dx, isn't it? Is it okay?
Yeah.
Fine. So now if I want to perform integration for C, your p dx. So this is simply C1 p dx plus C2 p dx, C3 p dx plus C4 p dx. Okay, fine, isn't it?
Yes.
Okay, so now you can see that, I mean, along your C2 and C4, along C2 and C4, x is constant, isn't it?
Yeah.
Fine. So that means your this dx, this is going to be 0. Fine.
Yeah.
Okay. Now, if I consider this curve, this curve from the point A to the point B, I mean, whose x coordinate is A and B, from those 2 points. Okay. So then, what it is going to be, like say, in fact, your G2x, if I look at the orientation from left to right, so it is along the curve minus C3, isn't it? Because the orientation of the curve C3 in the other direction,
Yeah.
isn't it?
Yeah.
Right? If I consider this curve in the increasing direction of x, so that is going to be minus C3. Is it okay? Fine.
Yes.
So that means, thank you. So that means I can write this as C1 p dx plus your if I adjust it, it is going to be minus C3 p dx. Isn't it?
Correct.
Fine. So but C1 is G1x and C3 is G2x, isn't it? Right? And for integration with respect to x, the lower limit and upper limits are a and b. So what is going to happen? For these two, I mean, for the first one, can you see this? Okay, maybe I will write it here. So this I can write as AB, say this is gx, and for this one I can write p x, c1 corresponds to g1x, okay, and then similarly for the other one, this is p your x g2x. Fine. Okay, so you can see that, I mean, this is nothing but minus of this. Yeah, this is nothing but minus of this. Is it okay? Fine.
Correct.
So similarly, you can prove the other part. Other part means you can prove that your q dy. So this is d dA. If you consider your d as a type 2 reason, you can easily prove that. Okay, so that you can do at home. Okay, so this is about your Green's theorem. So basically, what is Green's theorem doing? You can convert a line integral into a double integral, or vice versa. That is what it does. Okay, line integral into a double integral, or double integral into a line integral. So you may be asking me why? What is the utility of that? See, you shouldn't think that. I mean, line integral is going to be always easy to compute. It is not like that. Or double integral is going to be much easier to compute than line integral. It is not like that. It depends upon the situation. It depends upon what kind of integrand you are dealing with. Okay, so this is where this is going to be useful in the sense that, I mean, just by looking at the situation, either we are going to convert a double integral into a line integral, or line into a double integral. Okay, so let us try to work out a couple of examples. Okay. What do I have? Okay. So yeah. Suppose you have to evaluate this. dx plus xy dy, where your C is the triangular curve. C is the triangular curve where the sides are. C is the triangular curve where the sides, they are nothing but line segments. It is given by these 3 points. So lines from 0, 0 to 0, 1, and 0, 1 to just 0, 0 to 1, 0, and these two 0, 1 and 1, 0 to 0. Okay, so basically what is being given, that we are considering this triangle. We are considering this triangle. So your C is this. Your C is this curve. Although this is in the shape of a triangle. This is your C. This is your. Should I write? I mean, okay. Anyway, you should that blue. Curve is C. Okay, because if I specifically designate one as C, you may be thinking that okay, only that portion is C. Okay, and this shaded portion, this is D. So here, obviously, see this, the intercept is 1, 1 from both sides. So the equation of this particular portion, it is x plus y equal to 1, or your y is 1 minus x. Okay, fine. So obviously, this is what?
Both
This is a
type 1 and type 2.
In fact, it is a simple reason. It is a simple reason. It can be expressed both as a type 1 and type 2. See, even if it is not, I mean, the condition for Green's theorem requires that you should have a what? Simply, you should have a what? Simply connected reason, right? Isn't it? You should have a reason bounded by a simple closed curve.
Yeah,
Isn't
yeah.
it? It doesn't say about simple connect. Yeah, and that curve has to be, I mean, positively oriented. That's it. It doesn't matter whether it is a simple region or not. But in this particular case, it is a simple region. Okay. So then I mean, if I use for this, here P is x to the power 4, Q is xy. So if I use Green's theorem, what I am going to get del del x of Q. Q is here xy minus del del y of P. P is x to the power 4, right? And then dA. Okay. So now let us see what it becomes. I mean, it is going to be simply y, right? Simply y. So now, if you look at this, if I consider it as a, I mean, type 1 region, so then obviously the range of x is going to be from 0 to 1, and y is going to be y is equal to 0, bottom and top. Top is 1 minus x. So basically, what I'm going to do dy. So y goes from 0 to 1 minus x, dx, x goes from 0 to 1. And this you can easily calculate, isn't it? So 0 to 1, this is going to be y squared by 2. So it is going to be 1 minus x whole squared by 2 dx. And eventually it is going to be 1 by 2 into 1 by 3 into minus 1, then I mean 1 minus x whole cube, 0, 1. Okay, so when it is 1, it is 0. When it is 0, it is going to be eventually 1, but minus sign will be there. So eventually it is going to be 1 by 6. That's it. Okay. And the next example then that I'm going to take, it is, I find it very funny, and all the students, I mean, you should remember that your instructors are going to, I mean, trick you with examples like this. Okay, so be careful about this kind of example. Okay, so here it is about evaluating you have to evaluate this integral, where your C is the circle, given by C is simply this circle. So basically, I am considering something like this. This is my B. This is your x squared plus y squared equal to 9. Okay, fine. So as before, I mean, if I use your Green's theorem here, since it satisfies, I mean, all the conditions of Green's theorem. So then this is going to be del del x of q. Q is here 7x plus y to the power 4 plus 1, and p is 3y minus e to the power sin x. Okay, and dA. Okay, so now interestingly, you can see here that this is going to give me simply 7, and this is going to simply give me 3, isn't it? So basically, I get a constant out of this, right? And this is dA, and since the region is a disk, what I'm going to do, I can simply use polar coordinates here eventually. Is it okay? Yes?
Yeah.
So now I don't know whether you have noticed the interesting part here. Okay. See here, this particular function, it has been constructed in such a way that, I mean, the part where only x is involved, I mean, that is pretty straightforward. I mean, you would have been able to, differentiate it partially with respect to x. I mean, if if this was a function of x. But if you look at the y part, it was pretty complicated here, isn't it? And but you know that derivative of that with respect to x partially, it is going to give you 0, right? Similarly, here you can see that the x part, it looks quite complicated. So the instructors are going to give you construct some complicated function of this. Okay, and at the first glance, you will see that, oh my god, this is so difficult, right? And even, like say, if you don't use Green's theorem, this would have been extremely difficult, I mean, integration to perform, isn't it? Fine? So that is where your Green's theorem is going to come into your rescue, okay? So now I've finished today's class with the I didn't do this one. I think you'll be able to perform integration, right? Isn't it? Because this is simply double integration of 4dA.
Yeah.
Okay. And again, now still sticking to that point, double integration of 4dA. So this would have been what? This would have been 4. Okay, now you know that if the integrand is 1, so it simply gives you the area of that particular region. Isn't it?
Yes.
Fine. So I would have simply got 4 into pi r squared, 3 squared. So 36 pi. I don't even have to, right? Use any r, d theta, dr, all this stuff. I don't even have to do. Okay. So on that note, let me come to the application of Green's theorem. Application of Green's theorem. So it has many applications. I'll show you a simple application here. See, as I had told you here, so you know that. I mean, if I consider a region D bounded by a simple closed curve C, so then what is going to happen? If I want to do, say double integral of this. So this is simply going to give me the area of the region D, isn't it? Is it okay? Fine.
Yeah.
So now, if I want to, I mean, construct it in the form of this, I have to choose P and Q in such a way that your del P del Y minus del Q del X, that becomes equal to 1. Is it okay?
Yeah.
So then I have got, many possible scenarios. But what I can do, I can think as P to be equal to 0, Q to be equal to minus X, isn't it? This can be one combination.
Yes.
Another combination could be, P equal to Y, Q equal to 0. Fine. Another combination could be your P equal to Y by 2, Q equal to minus X by 2. Right? So that is why this area, just a minute. This, in terms of line integral, if I want to express, so this becomes what? This becomes, say, dx. No, x gy. Sorry. or you may write it as your y dx, or you may write it in terms of half c y dx minus x dy. Isn't it? Okay. So I am giving you the homework. So I mean, using either of these three formulas, find out the area of the ellipse. This. So what I'd like you to do, you simply use this one. The parameter is this one. A cos t, y equal to b sin t, and your t goes from 0 to 2 pi. Okay, please use that, and then you are going to get the result. I think IAB or something like that. I actually don't remember. Okay, so please do that, and I think with that note, I'm going to finish today's class. So then I will meet you in the next class.